So for Unit 8, we're going to talk about mole and the chemical calculation that is related to the mole. These are the four bulletins that we're going to focus on. So we're going to look into atoms and the need for mole. So why do we use the unit mole specifically to describe the number of atoms? And then we'll look into the relation between moles and grams and how both are connected to each other. We'll also do some practice problems and some examples to convert between moles to grams and back grams to moles. And then we'll look into conversion between mole to mole. I know this may not sound that it makes sense at this point, but I think once we do some examples, you'll know exactly what I mean. And then we will finish Unit 8 with empirical formula, which I think if you have developed good understanding for the three first topics, which I hope that you would, and you know how to make ratios, I think understanding the empirical formula won't be that hard to understand. Okay. I think we talked about atoms last time was in Unit 2 or Unit 3 when we were talking about chemical bonding, and I would say one of the main features that probably stuck in your brain at this point is how small the atoms are. And we talked about how most of the mass of the atom is concentrated right in the nucleus, where you have the protons and neutrons, um, and with the electrons basically orbiting around the nucleus. With more electron density as you get closer to the nucleus, and less electrons as you move away from the nucleus, as you see in this drawing right here. Okay, the atom tends to have a diameter of zero point 0.1 to zero point 0.5 nanometers, so you can imagine how small the atom can be. What you see up here, this is the electromagnetic radiation spectrum, or the EMR spectrum, which really classify the radiation based on the energy. So, for example, if you look at the gamma ray and the X ray and the UV, the ultraviolet, those guys tends to have the highest energy. That's why when you go, for example, to the dentist, or you break your arm and you want to take an X ray, they make sure they put a sheet of metal over your body, because the X ray tends to have a really high energy, and it will penetrate through the human body, and it can be very disruptive to the human biology, to the cell biology. Same thing with the gamma rays and the ultraviolet. That's why we put the sensor cream, for example, because it is a harmful type of radiation. The infrared, the microwave, and the radio waves, those tends to have a low energy. That's why we listen to the radio all the time without really any chances of, any risk of being exposed to the radio waves, for example. Um, so the radio wave, the microwave, the infrared, this kind of radiation would have a really low energy or a low energy, but it would have a longer wavelength. I guess the relation between the atoms and the wavelength, and that's what I'm trying to convey here, that you can see that the human eye covers a range of 400 nanometers to 700 nanometers, right? With the atom diameter between 0 0.1 to half nanometers, you can imagine how many atoms would be in a wavelength, for example, of 400 nanometers. Hundreds, probably thousands of atoms. Same thing when you're looking at a 700, for example. There's even more atoms laid next to each other. Or as Einstein, refers to that one also as photons, and that's what the light consists of when it comes to, describing the light itself. Okay, so atoms are very small and tiny, and the study for the atoms, it started back in 1927 with a Robert Brown when he first studied the pollen particles, and he observed how the pollen particles will be jumping over off a surface of water. And in the beginning, he thought maybe because he was considering it as a living organism, that's why it's moving. Okay, but then later he also examined dust particles of the same size, and he noticed that the dust particles basically behave with a similar fashion. So that's the first observation for something as close as possible to the size of the atom. Now, obviously, the pollen particles and the dust particles are nowhere near the atom, because the atom is even smaller. Okay, and then in 1877 we have the kinetic molecular theory, which is something that we talked about extensively um, in unit. I'm going to say unit 3 and 2 and 3, I think, also, which really talks about how All substances or material consist of a very small tiny particles. These particles are in a constant motion. That motion depends if the material is a solid, liquid, or a gas, so on and so forth. Okay, and then we have Thomson, which he basically used. He used the Cook's tube to study the existence of electron by ionizing the content of that tube, as you see here. Let's see, on this tube. So he ionized a specific gas, for example, or it could be anything like a sodium gas or chlorine gas. The change in color that identified there's atoms and there is a chemical that is electronic chemical change that is taking place, and that was his observation to the atom in 1897. And then in 1905, uh, this is the big change here with Einstein theory when he proved the existence of atoms and electron using mathematical equations at that point, which obviously was a breakthrough in 1905. And then in 1911, Rutherford he used the radiation to identify the protons in the atom, the protons and neutrons. That was in 1911. So in 1927 or 26, John Pern he was able to approve all Einstein's findings using the ultra microscope. So every all the theories that Einstein has proposed when it comes to mathematical proof of the existence of atom and the electron behavior, John Pern he was able to basically prove using, like I said, the ultra microscope. In 1981, Gerd Benning and Henrik Rohr at IBM, they invented the scanning tunneling microscope, so they were able to take a better image for the atom, more detailed image for the atom, and that's for the obvious reason for IBM, because those guys, they always look to make things smaller, more efficient. If you think how big the computers used to be in 1991 and 1981 compared to now, that explains why IBM is interested in such thing. Up until nowadays, there are many technologies that have been developed, from 1981 up until now, including X-ray crystallography, NMR. Some of those technologies are really common nowadays to use by labs every single day to study the atoms, molecules, and identify and use these technologies to identify atoms and molecules. So even though atoms and compounds are very small, counting how many atoms you have or how much of that compound you have, it's very important, especially when it comes to something like drugs, for example, where all these pharmaceutical companies, they would focus all the time to know exactly how much they have of the active ingredients in their drugs, so they make sure they are not overdosing their patients, for example, or they're not designing a drug that will not be effective at treating pain, for instance. So they need to know exactly how much they have of their active ingredients molecule. Same thing when you're giving oxygen to a patient of 180 pounds. You need to make sure that you're giving concentration enough of oxygen so that person will not have a heart failure. Even something as trivial as shampoo, for instance, the shampoo that we get from store. So these detergent companies, Unilever or Sun, they need to make sure that they're making a shampoo or a detergent or any other cosmetic product that have enough chemicals to be effective and serving what the customer is expecting, but not have plenty of chemicals or high concentration of chemicals that would cause, for example, would be corrosive to the skin or cause some, skin reaction or allergic reaction to the customer who's using it. So, counting how many atoms and counting the mass of your compounds, it's very critical when it comes to industrial chemistry, when it comes to chemistry in general. How do we know how much we have? By weighing. Even though we're talking about atoms and compounds, which is a very small amount, we are going to establish a relation between weighing and knowing exactly how much you have of the atoms. And for that, what I will do, I'm going to start with an example of nails. Okay? And then from that example, we are going to draw and kind of have a comparison relation between nails and atoms, so you guys are able to understand how we can count how many atoms we have by just weighing. Okay, so what I will do for the example of nails, I'm going to use grams, and that's the same unit I'll be using later when we're talking about mass or weighing for atoms. So let's say, for example, you go to the Home Depot and you grab 100 nails. When you get those 100 nails, you decided to weigh every single one, and then you realize there is 82 nails of those 100 that actually weighs in 3.8 grams each. 14 nails, every one of those 14 nails would weigh in 3.7 grams, and the last four would have 3.6 grams each. So the mass of all those nails throughout the 100 nails are not consistent. 82%, because when we say 82 of 100, that means 82% of those nails would have 3.8 grams. And then 14% will have 3.7 grams. And then 4% is a 3.6 grams. Okay, so in order for us to come up with an average mass for the nail, for a nail within this 100 nails, what we need to do is we need to multiply the 82% times the mass of that 82%, which is 3.8 grams each, and then you add that to the 14% multiplied by the 3.7 grams of the mass of every single nail within that 14, and then 3.6 grams multiplied by the 4% at which these 3.6 grams nails are represented within this 100 grams. In average, we have 3.78 grams. So, for all these 100 nails, the average mass for a nail within this 100 nails would have a mass of 3.8 grams. So essentially what I did, I created a conversion. My conversion is every one nail will have a mass of 3.7, 3.78 grams. My conversion indicate a relation between count and weighing. In other words, I can use this conversion by weighing any amount of nails on a scale and use this conversion to convert and find out how many nails I have based on the average mass or the average weight of that nail. Okay, let's look at this example down here. So the conversion factor from weight average can be used to make conversions between mass and number of object. So let's say, for example, I went to Home Depot and I grabbed myself 218 pounds of nails. Okay, I would like to convert this 218 pounds of nails to how many nails I have within that specific mass. Well, first, my conversion is gram per nail. So what I need to do first, I need to convert my pounds into grams. And that should be an easy peasy because we know we convert between the SI system and the English system by 1 pound equal 453.6 grams. So the pound, will cancel out with the pound. Now I have a grams. The grams is going to cancel out with the grams. So you multiply the 218 with the 453.6 and you divide that by the 3.78. You will find out that in 218 pounds of nails, you have 2.62 times 10 to the power 4 nails. Okay? Now, if I go to Home Depot and I say, well, can you get me 2.62 times 10 to the power 4 nails? The guy at the Home Depot aisle, he would have a reaction of, what are you nuts? What are you talking about? What is 10 to the power 4? That's why we call this a scientific notation. And you guys should be all able to convert between numbers and use the scientific notation to represent your represent your numbers. So these large numbers, going back to the person at a Home Depot aisle, they're not sure about the 2.62 times times 10 to the power 4. That's why we have new terms that we use to represent large numbers. So, for example, we use a 12 to represent a 1 dozen. So, in every 1 dozen, there's 12 units. Or we use a gross to represent 144 units. So, in every 1 gross, that is 144 units. So, for example, if I want to convert the 2.262 nails to a gross, what I need to do is I need to start again with 218 pound, convert that to grams, and then convert that to count of nails, and then basically take the 2.26 and then multiply that by 1 gross nails, 144 nails. So the nail will cancel out with a nail. And then you will end up with 182 gross nails, which would be a number that it's easily understood by, by an average person probably. Okay. Just like with the dozen and a gross, a mole is equals 6.022 times 10 to the power 23 units per mole. It doesn't matter if we're talking about atoms. It doesn't matter if we're talking about nails. It doesn't matter if we're talking about candies. For every mole, there is 6.022 times 10 to the power 23 units. And I would like you to keep that in mind and always remember this. So atoms are so small and numerous that they cannot be counted directly. We need a conversion factor that converts back and forth between mass of an element and the number of atoms contained in that mass. Okay? So let's use a convenient units for measurements. What we use is we use the atomic mass, and we abbreviate that as U. For example, if we're talking about carbon, which has an atomic mass of 12, and that's because it has 6 protons and 6 neutrons. Now, granted, also it has 6 electrons, but electrons, it's not really counted within the mass of the element because, as we said earlier, only the nucleus that basically represents the mass of the atom. So 6 protons and 6 neutrons, that represents 12 units or 12 atomic mass units. Okay? To determine the mass of the individual objects being measured for the carbon, there is 98.90 of the carbon that has a 12 atomic mass unit. But in the same time, there is a 1.1 that has a 13.003355 atomic mass units. And that's what we call isotope. If you remember when we talked about isotopes back in Unit 2, I believe, or Unit 3. Okay? So this is very similar to the nails example, right? When we grabbed those nails, we'll realize some of those nails has a different mass. Same idea here with the carbon. Most of the carbon has a 12 atomic mass unit. That is 1.1 has a 13 atomic mass unit. So what we need to do, we need to calculate the average mass for the atomic carbon. How do we do this? We multiply the percentage, which is 0.989 times the 12 atomic mass unit, and you add to that one the percentage of the 13 atomic mass unit. You add them together, and you will end up the average mass for elemental carbon. So for every atom of carbon, there is 12, or every atom of carbon would weigh in 12 atomic mass unit, 12.011. And that's the number that you see in the periodic table. Okay, so here is our relation between the mass of the atom and the count of the atoms, right? From this conversion, I can, if I know how much I have of the carbon, I can convert that to counts of atoms of carbon for carbon. Okay? So we describe the number of objects in terms of a collective unit and use this and the weighted average to create a conversion factor to make conversions between mass and the number of objects. And that's what we refer to as mole. So when we're counting atoms based on early experiments with hydrogen and then oxygen, then carbon, it was determined that for every 1 gram of hydrogen, it will contain 6.022 times 10 to the power 23 atoms. Now, what does this number represent? 1 mole, right? For 6 grams of oxygen, for 16 grams of oxygen, it contains 6.0222 times 10 to the power 23 atoms, which also 1 mole. So what I'm essentially saying, and also for the carbon, 1 mole. So what I'm essentially saying here, that for every 1 gram of hydrogen, there's 6.022 times 10 to the power 23 atoms. And then for the oxygen, every 16 grams of oxygen would have 6.022 times 10 to the power 23 atoms. And then for carbon, for every 12 grams of carbon, there is 6.022 times 10 to the power 23 atoms. So this serves our conversion factor between grams of carbon and units count of atoms for the carbon. So you can weigh in any mass of carbon and you will be able to count exactly how many atoms exist in that specific mass. So the mole is an amount of substance that contains the same number of particles as there are atoms in 12 carbon of carbon 12, 12 grams of carbon 12, okay? So a mole equals to 6.022 times 10 to the power 23. And this number, this constant number, I will give it to you during the exam, so you don't have to worry about memorizing this number. We call this number as Avogadro's number. So Avogadro's number is 6.022 times 10 to the power 23. And this number is used to describe the number of atoms. So for example, to see how extremely small the atoms are, if you take 12 grams of carbon and arrange all the atoms within that 12 grams of carbon right next to each other, it will extend over 500 times the distance between Earth and the sun. Okay, so that's how small and tiny the atoms can be. So Avogadro's number, which is the 6.022 times 10 to the power 23 atoms, basically represents what's equal to the number, or what's equal to the term dozens or gross, the one that we just talked about earlier. Chemists use the Avogadro's number as a way to represent the number of atoms. Okay? And in every 1 mole of a substance, I might have mentioned that before, there is 6.022 times 10 to the power 23 atoms. Okay? This is a constant figure that never changes based on the elements. So if you're talking about a gram of oxygen, or you're talking about a gram of carbon, of hydrogen, or silver, it doesn't really matter. Or a mole, I'm sorry. If you're talking about mole of oxygen, or a mole of silver or gold, a mole will always have 6.022 times 10 to the power 23 atoms. Okay, so for example, how many cinnamon raisins in a bagel in a dozen? There is 12. How many egg bagels in a dozen? There's 12. It doesn't matter what kind of bagel I'm talking about. It's about the term dozen. The term dozen represents 12 units. Okay? How many carbon atoms in a mole? 6.022 times 10 to the power 23 atoms in a mole of carbon. How many oxygen atoms in a mole? Same thing. 6.022 times 10 to the power 23 atoms. How many bagels in a mole? 6.022 times 10 to the power 23 atoms. Now, obviously, we don't use mole to refer to count or number of bagels, but just so you can get the idea. Okay, so the mole represents 6.022 times 10 to the power 23 atoms, regardless of what element you're talking about. Okay, so now that we can convert between moles and number of atoms using Avogadro's number, let's look at the relation between moles and grams, because if we can convert grams to moles, we can easily convert the moles into number of atoms. Okay, so that's what we use, what's known as the molar mass of an atom, and we can get that always from the periodic table, and that's the same thing as the atomic mass unit that we looked at. If you look at the periodic table now for the hydrogen, for instance, you will see this number down here, which is something that we talked about multiple times as the atomic mass unit. Okay, so what this one basically represents, or what this one tells us, it's another way of representing a conversion factor for the hydrogen atom. So we can say every 1 mole of hydrogen would have a mass of 1.01 grams. Same thing with the oxygen. For every 1 mole of oxygen, it will have a mass of 16 grams, or 15.99. And I can use that as a conversion, so as a conversion factor. So I can either say every 1 mole of oxygen will have a 16 point or 15.99 grams mass, or what we can say also, we can say 15.99 grams of oxygen would be equivalent to 1 mole of oxygen. This conversion factor, the way to write this conversion factor, it really depends about the process of your conversion and what are you trying to convert to. So if you're trying to convert to moles, for example, you'll have to cancel the grams. If you're trying to convert to grams, then the grams will be in the bottom and the moles will be up there, so you can cancel out the moles, so on and so forth. Now, the fact that I can convert between grams to moles, and I can convert between mole, every 1 mole equals 6.022 times 10 to the power 23 atoms, I have established a relation between grams and atoms, number of atoms, because I can convert grams to moles and moles to atoms using Avogadro's number. Okay? So to put things in perspective, if we're talking about 1 mole of carbon, which would be equivalent to 6.022 times 10 to the power 23, would equal to 12 grams of carbon. Okay? Which is going to be equivalent to 60 carat pink star diamond. If you're talking about 1 mole of carbon of gold, for example, 1 mole of carbon of gold would have, again, same number of atoms, which is 6.022 times 10 to the power 23 atoms of gold, but that one would have a mass of 200 grams, because gold is much heavier than carbon. Okay, likewise with the helium, 1 mole of helium would have the same count of atoms, which is Avogadro's number, but that one is very light. That's why helium goes up in the air. It's 40 grams. Okay, so you can see 6.022 times 10 to the power 23 atoms of helium has a mass of 40 grams, while for gold it's 200 grams. That's why when you put a plate of gold on your hand, you can feel the mass of gold, because it's a very heavy atom. Now, why is it heavy? Because of the number of protons and neutrons in the nucleus. You have 79 protons in the nucleus, while you have 2 protons in the nucleus. Okay? That's where the big mass comes from. So, let's do an example, moles and grams. So, boron is used as a neutron absorber. So, it's used in nuclear reactors to absorb any excess of neutrons to eliminate any radiation. Okay, it is also used to make a semiconductor, and also as and rocket propellant. So first, what we will be doing is we are going to write the molar mass for boron as conversion factor that can be used to convert between grams of boron and moles of boron. Then we'll have to calculate the mass in kilogram for 219 moles of boron, and then I'll have to calculate how many moles of borons in 0.1532 pounds. Okay? Now, if you pull your periodic table now and you try to locate boron, what you'll find boron with a symbol B, with 5 representing with as the atomic number, which means the number of protons, and as well as the number of electrons for neutral boron. And down here, I'll have 10.811, which is the atomic mass. The unit for this one is a gram per mole, as we said earlier. So this essentially answers my first question here, because the question says write the molar mass of boron as a conversion factor that can be used to convert between grams of boron and moles of borons. So we say mole, every 1 mole of boron would have a mass of 10.811 grams. So that's my conversion factor. This is the formula that's used to convert between grams and moles of borons. Now, the next question asks to calculate the mass in kilograms for 219.9 moles of boron. So I need to put this formula here in application so I can convert the moles into grams. So what I'm starting with 219.9 mole. And I'll multiply that by my conversion factor, okay? But in this case, I'm going to have to flip my conversion factor again. Remember, this is not written in stone. You can always change the moles and the grams. So the grams can be in the denominators, the mole can be in the denominator, based on the required unit for your conversion. So in this case, because my goal here is to get kg at the end, which means I'm trying to convert to grams first before converting to kilograms. So grams has to be in my nominator, and mole has to be in my denominator, so I can cancel out the moles later. So this one will be 10.811, and this one will be 1 mole. I'm not finished yet because I need to convert the grams into kg, into kilograms. And we know from our metric system that a 1 kilogram would equal to 1,000 grams. So now my moles cancel out with a mole, the gram cancel out with a gram. Now you multiply everything together, you crunch it into your calculator, this will be equal to 2.38 kg, okay? So 219.9 moles of boron would equal to 2.38 kilograms of boron. All right, let's do it the other way around. Now, the next question asks for how many moles of boron in 0.1532 pounds. So I'm starting with a mass. I'm going to have to convert to moles. So what I will do is I'm starting with 0.1532 pounds. First, I'll have to convert the pounds into grams, again, using my metric system. So I have pounds, metric system to the English system, 453.6 grams. So now the pound can cancel out with the pounds. And then I can use my conversion factor up here. Do I need to flip and change my moles and grams from being a denominator to being a denominator? No, I don't need to do any of that because I need my grams to cancel out my grams later and moles to be my unit in my final answer. So this one will be 10.811. So pound cancel out with a pound, gram cancel out with a gram. You put all these numbers in the calculator, and a number of moles that is equivalent to the 0.1532 pound of boron would be equal to 6.43 mole. Now, we are going to take this a step further, I think, in a couple examples later, but I can convert, 3 mole. Again, I can convert this number of moles to number of atoms, right? Because we know in every 1 mole, that is 6.022 times 10 to the power 23 atoms. Okay? So if you multiply the 6.8 or 6.43 times 6.022, that would equal to 3.87 times 10 to the power 24 atoms. So we can convert from pounds to number of atoms to know exactly how many atoms of boron we have in that 0.1532 pounds.